In this video, we get into the guts of the Fourier series. All the guts. For a square wave, or for 2 or 3. But here's the first one, from negative L to L. Fourier will recreate this function with sines and cosines, and this function again goes on forever. We're just looking at it from negative L to L, term after term after term. 1, 2, together. 3, together. The square wave we saw in part 1. So let's get to it. Let's get to A0, AN, and BN. No, wait. First we'll need some tools. Odd and even functions. The sine wave is an odd function. It's been called worse. The cosine is an even function. What's the difference? Well, when an odd function is integrated around 0 here from negative a to a, the answer is 0. That's not true for even functions. But it is true when an even function is multiplied by an odd function. Those kinds of symmetries cancel out. Take my word for it. But that's not true when an odd function is multiplied by another odd function. In that case, it acts like an even function. Switches. We've seen these before. Remember the power series expansion for sine. Minus, plus, minus, plus. Our Fourier series, some of them anyway, will do stuff like that with terms like this, which we've seen before. And we can control. That's what a switch does, after all. It controls stuff. On-off switches. A little bit more complicated, but it still works. It can work with trig functions too. Give yourself a moment here. Positive, 0, negative, 0, positive. Can you make an expression that gives you a pattern like that? We'll try this one, or that one, which is a little shorter and easier. But they both work, I promise. Which is what we needed for our sine wave. Remember that? See, no even terms allowed. Integration by parts. We'll hold off on that one until part 3. But we should say a word or two, however, about sines and cosines. You'll see this in every Fourier series, n pi x over L. And we want to integrate. 1, 2, 3, 4. Fourier. With these terms and this function, A0 is 0. Well, we know that because our function is odd. Or you could work out the integral, or you could remember what A0 means. It's the average height of the function. 0. AN is also, hey, it's an odd function. It's 0. An odd function, it's 0. BN is not 0. And we will need to get to work. I probably should have used that trick where I could multiply by 2 and change the integration limits from 0 to L. Next time I'll do that. Okay, well, here we are. The trickiest part of the whole operation. Remember that the cosine of 0 and the cosine of 2 pi is 1. The cosine of pi, the cosine of 3 pi, the cosine of 5 pi is negative 1. See what I'm saying? The integrals give different results depending on whether n is even or odd. Now this really takes 2 seconds to look at it. So think about it, or don't, because we're done. Fourier is solved. A0 is 0. AN is 0. BN is that. FX is that. To the spreadsheet. Amplitude. Could be anything we want. I let L equal 180 for these waves, even though x goes from negative 250 to 250. That means we get a little bit less than a half an extra cycle. We get more than just one cycle on the graph. I think it looks better that way. Anyway, here's the n values. Those values we can change. And a formula for the first half of our Bn term. And the second half just turns the function on or off. This would give 0 when n is even. The sine n pi x over L term. This is the big deal about Fourier. All the x's are only inside sine and cosine functions where they belong. All together. And then repeat for other n values. Term after term after term. Term after term after term. Square wave. Eventually, square wave, and made with sine waves. Or, as we saw in part 1, we could make these with up and down Epicycles. Think about these epicycles. What are they doing? They are going up and down in time. That's what the sine wave does at different frequencies, at different amplitudes, but they're doing the same thing. Still have those tools? Good, because we have another wave to do, which is really just the same wave, but it's different also. This time we're looking at a window from 0 to 2L, not negative L to L, and this function goes from 0 to A, not from negative A to A. So okay, let's find A0 and AN and BN. A0 is not 0 this time, and that makes sense. It's the average value of the function. It's A over 2. What about AN? Well, our function isn't exactly odd, but I guess it's close enough to being odd because when multiplied by the cosine and integrated, 0. Bn, again, that's where all the action is, and like the first square wave, the Bn term disappears when n is even. We're moving faster here, but putting it all together, and the equation is the same and different. Let's take a look at the two compared to the first wave. The second one is shifted up by the A0 term, and it's only half the total amplitude, and also it's inverted. And notice that the first wave was at a maximum from 0 to L, the second wave is at a minimum. And yeah, it's kind of messy, but we can control it. And one final square wave and a new thing to control, K. We can now scale the size of the peak anywhere from 0 to L. Try not to let the power go to your head. Well, there's the function. Clever use of the absolute value there, well done. And 3 terms to find. A0 works out to be AK over L. Again, the average height of the function. I like that. That's easier to think about than doing the integral, but it is what the integral is. Okay. Bn, we're skipping to Bn. Because Bn is 0. Our function this time is even. And the sine wave is odd. And there you go, An. Using the trick of multiplying by 2 and integrating from 0 to k. Is that it? Yeah, we're done. Fourier becomes solved. And notice that something special here happens when we set k is equal to L over 2. We get our square wave back. And sine n pi k over L becomes an on-off, positive negative function. But the whole point here is that we could let k be anything from 0 to L. And we could put it in our spreadsheet. We set L to 180, so we'll start with k as 120, A0, Bn part 1, Bn part 2, the cosine term, and putting it all together for n equals 1, and then we'll do the same for other n values, and we'll get this plateau. This is for n up to 5, n equals 5. Remember that 2 and 4 are 0, so this is up to n equals 5. And remember that L only goes to 180, and we're going here to 250, so we're beginning to see the next plateau here, 2, and there, 3. And here, k is equal to L over 2. Okay, and here is a smaller k, a narrower peak. And keep in mind what we're doing, it's kind of a lot. We are changing k and finding values for different n terms, and then adding those together and putting them together for different x values. And it seems like we are inching our way ever closer to being able to put Paris into a cosine.